Had, can you explain briefly what we study in previous class?
Sorry, sir, I forgot.
Okay. Saad, do you remember? Anyone? Anyone remember what we study in previous class?
About the performance of solar energy system.
Okay. So which method we have studied up till now?
Don't remember.
Okay, let's continue. Basically, in previous class, we study the long-term performance of a solar energy system, and we estimated a performance index. It's called solar load fraction, right? Uh, it could be on monthly basis and it could be on the annual basis. Annual is the weighted sum of this one. I mean FILI, FILI, and I mean sum of this and sum of Li. So this is weightage average. And we have discussed the simulation method, F-chart method. So remaining, the next one was a utility method. It is also called phi bar F-chart method. So let's start with the utilizability method. Uh, to discuss this method, we first have the concept of phi. What is phi? I mean the utilizability, right? Uh, I mean, why we need the next method to discuss? Because there are certain drawback in the F-chart method that we discussed in the previous class. One of the drawback in F-chart method is it is only applicable where the temperature is close to 20 degrees C, or we can also say when we need to analyze with a constant inlet temperature of the collector. But actually, we know that in collector, when we, I mean, when we deliver water, let's say to a storage tank, then again from storage tank the water comes in to the collector. So the inlet temperature actually it is varying with the passage of time. It is based on the load. So that's why F chart method is limited for the when the temperature is very close to 20 degrees C, right? And we also have many application where we need a temperature which is higher or lower than the 20 degrees C, right? So there are many. I'll give you a few example. For example, if there is a warehouse where we have stored things and the heating system is required to keep the building above the freezing temperature. I mean, we don't want the items or the things that we have placed in the warehouse to be in freezing condition. So that's why we need the temperature above than the 0 degree C. So that could be one of the application which is I mean away from the 20 degree C, but we can utilize that energy. And similarly, I mean there is an air conditioning process that we also study in today's class that they call the absorption cycle. They are operated using the solar energy, and the temperature is requirement is much higher, about 70 degrees C, sometimes 80 degrees C. So that means we need the high energy temperature. So that means to analyze such system, the F-chart method is not appropriate. So we must have a system, a generic system that can deal all range of the temperature. So the answer to that is utilizability method. In that method, the concept of utilizability is integrated with the solar load fraction. So let's first discuss what is the meaning of the utilizability. Now in the phi, utilizability is basically, we can understand this, that we know that the useful gain, I mean QU, useful gain mean the QU, right, is the difference between the solar energy absorbed and the thermal losses from the collector. I mean, if you have a collector, right, the energy absorbed, right, right, and it has two part. One is the Q losses and one is Q useful. So that useful gain is basically the difference of the energy absorbed and the losses from the collector. right? There could be a value that the incident radiation, I mean this incident radiation is just enough so that the absorbed radiation equals the losses. I mean, let's say there the second condition is possible that if you have a collector and the amount of the solar energy absorbed is just enough to compensate the losses only, right? I mean QL, this is equal to QL only, right? There could be a situation, right? So that value of the incident radiation is called critical radiation level, right? This is very important. That's called ITC. So when we say the critical radiation, so that radiation is when the incident radiation is just enough to compensate the losses only. So that level of the radiation is called a critical radiation level, right? So then we can, define the phi value or the utilizability. This is basically the fraction of the total radiation that is received at an intensity higher than the critical level, right? Let's say this is the 12 hour of the day, and you know that from sunrise to sunset there is a flux of the sun which is incident on, let's say, on a solar collector surface. At noon we have the maximum value of the flux. Now you can see, let's say the critical level of the radiation is this one. I mean, this is the level of the radiation which is just enough to compensate the losses. That means below than the critical one, below than the critical level, that's not useful. Actually, the useful energy will be above than the critical level, because this portion will be just utilized to compensate the losses only. So the above than the critical level, that will be basically utilized for the useful gain or the useful heating. So that's why we can define phi. I mean, this is phi is fraction, right? That's the fraction of the total radiation that is received at intensity higher than the critical level. So whatever is this area? So let's say this is let's say the area basically represent the amount of the energy. So let's say this is A1 and the total area is, let's say, A. So the fraction of the radiation which is above than the critical level to the total radiation. So that's called the utilizability. Now, if Now, if IT, I mean the total energy absorbed, is greater than the intensity of the critical radiation, then there will be useful gain and the collector should be operated. I mean, this is the condition where the collector should be operated. When you have the absorbed intensity of the radiation is larger than the critical radiation, at that time the collector will be operated, right? And if the incident radiation or the absorbed radiation is less than the critical radiation, that means you cannot got any of the useful gain, right? So therefore the collector should not be operated under these conditions, right? And there is basically the hourly utilizability. I mean, you can define instantaneous, but obviously when you evaluate the performance of a system, it could be based on the hours, daily basis, or the monthly basis, right? So this is one of the utilizability. It is called the hourly utilizability. So according to this is the fraction of an hour's total energy that is above the critical level, right? For that particular hour. You can see here, for example, the total solar radiation variation along with the time. You know that from sunrise to the sunset, it is like that. But if you take any of the hour, let's say this is for 1 hour, let's say 10 a.m. to 11 a.m., right? And this is the critical radiation level of the critical radiation. So that means basically when we say the utilizability between that hour, this is the portion of the radiation which is, I mean, you can use for the useful gain. So when we say the uh, hourly utilizability, so this will be based on this hour only. So this fraction divided by the total radiation. As you can see, This is basically the IT mean the total incident radiation minus ITC mean, I mean the level at the critical a critical radiation level divided by the total. So that's called the hourly utilizability. Now the utilizability for a single hour is not useful. I mean, when you say the long-term performance, so I mean, to evaluate for just a single hour is not useful, right? So therefore, uh, we can extend that use. I mean, the performance in terms of the utilizability in terms of number of days for a particular month, right? Let's say uh, this is the hour, let's say 10 a.m. to 11 a.m. Let's say this is for the January month, for the complete January month. So similarly, maybe for the next month. So based on the weather data, we know that basically when is the uh, I mean operation time. I mean operation time mean let's say this is the solar flux. Let's say this is the solar flux. Now it depends on the critical radiation level. For example, the critical radiation level is this much. Let's say this is the critical radiation level. Now the useful gain is now this one, and the operation time is between this one. Now the operation time is this one, right? But if your critical radiation level is higher, let's say, I mean to compensate the losses, critical radiation level is let's say this much, right? Now your operation time is only this much, right? So that means higher the critical level, less useful gain will be obtained, and similarly the operation time will be smaller, right? So that's why for the long term we can define utilizability in terms of number of days, right? So n is basically the number of days. Let's say for a particular month, let's say 31 days are in a January, so we can have n maximum n equal to 31. So this will give you the monthly utilizability between that particular hour. And from this equation, if you multiply n and this average IT, when you take the average, you put a bar on that. So the remaining will be, this is the average of the IT minus IT. That's called the month's average utilizable energy for that particular hour, right? So you can also calculate that for that particular hour, what is the average utilizable energy by calculating the value of phi. Then there is a term we called critical radiation level. As I defined, that is represented with the term XC, right? So this is basically the radiation. I mean this is basically the dimensionless, right? We know that ITC. I mean it is basically ITC is the radiation at critical level, right? But we can make it as a dimensionless by dividing with the average absorbed radiation on any particular surface. That could be the tilted collector or the horizontal collector. So we called it as a critical dimensionless ratio, right? So a dimensionless critical radiation is defined in terms of by dividing with the average solar radiation. And if we know the value of the XC, I mean, from this graph, we can see this graph is basically adopted from the Liu and Jordan, 1963. I mean, this graph is basically used to calculate the value of the utilizability. If you know the value of the XC, you can calculate the value of the phi. Now, let's come back to the now we can discuss the phi F chart. Phi bar F chart. I mean, how to long-term evaluate the performance of the solar heating system, right? Basically, this chart, as I mentioned in the previous chart, that was also derived from the correlation was derived from a large number of simulations. So similarly, these correlations are normally derived from a large number of simulations. So the phi bar F chart was presented by Klein and Beckman. I mean, the author of this book in 1979. I mean, through many detailed simulation of the system, and he presented that the solar load fraction can be represented by this correlation, right? And as you can see now, previously when we study the F chart was just the function of two variable only. One was PL, another was PS, right? PL was load factor, load parameter, and PS was solar parameter. I mean, PL basically that was the representation of how much energy is lost, and similarly the PS was the representation of the how much energy is absorbed. And these two parameter was basically a function of many parameter, including the solar collector parameters, characteristics, and even the ambient temperature, weather data. So likewise here the solar load fraction is also a function of, you can see this is the phi max, and this is another parameter y, right? This is an implicit relationship, not the explicit one, because f is again a function of f. That means, and similarly x bar and rs, right? So you can see here now the load fraction is a function of four variable: x bar max, y, x dash, and rs, where rs is basically the storage capacity of the collector, right? This is the storage capacity of the solar heating system per meter square of the collector area. And the first one we call the phi max. When will be the phi, the value of the phi, I mean the utilizability will be maximum? What do you think? When the phi max will be maximum? I mean, in relation with the critical radiation. Anyone? When the phi will be maximum?
When critical radiation will be lower, or the radiation losses will be lower, and the incident radiation is higher.
Yeah, you're right. Basically, phi will be maximum when the critical radiation is minimum. As I explained with the help of the diagram, that when the critical radiation level is minimum, then you have more energy to convert into useful work. I mean, the losses are, I mean, critical radiation is a representation to compensate the losses. So phi will be maximum, xc, I mean, defined in the previous slide, is minimum. So xc, I mean this phi value, basically we can calculate that was represented by these Klein and Beckman with the help of some coefficient a, b, rn. Rn and r we have defined in the previous class as well. Xc is the I mean dimensionless critical radiation, right? But this is average on the monthly basis. Similarly, c is another coefficient, right? So that means to get the value of the phi, we need xc minimum, right? If you want here phi max, that means we should have the xc minimum, right? And xc is, we can calculate with the help of this formula. This is a function of the, I mean the heat removal factor, the load coefficient, the minimum temperature that is required, the average ambient temperature, right, and the average product of tau alpha, right? These are the parameters related to the solar radiation, and based on the location as well. We have also defined KT in the previous class. In the previous class, even HO we have defined in the previous class. This is the extraterrestrial radiation. This is the sky clearest index factor, right? This is again a factor, and we have defined these in the previous class, right? So this Rn we can calculate, that's the ratio of the I total to the I, right? I mean this is further equal to in the form of the diffused radiation, right? The total terrestrial radiation. These values basically we have defined in the previous class. I hope you remember that. This is rho g is the density of the grass, because we have the radiation in three form. One is the beam radiation, diffuse radiation, and reflected radiation. This D is basically for diffused radiation, and this rho g is from the ground, because when the solar collector is installed there, I mean the reflected radiation from the ground is sometimes you consider that factor, right? Even you can ignore this factor. So rho g is basically the density that you normally include, and the value when the grass is there, we normally take 2, and when there is ice, I think we take that value equal to 0.1. I forgot that, you can verify again. So you can calculate the value of Rn. Along with the Rn, what you need else? I mean, you need these parameter A, B, C, and these parameters, they are a function of KT, and we have defined how to calculate KT in the previous class. So you can calculate A, B, C, and the minimum critical radiation and the value of Rn, right? And then you can also calculate the value of R with the help of this formula. Right. And then since after calculating phi max, you can calculate the value of y. Right. Y is basically similar to PL. Sorry, PS. I mean, in case of is very almost the similar one. You know, this is the area of the collector. This is the heat removal factor, the product of tau alpha, and this is the average monthly total terrestrial radiation. This is the number of days of that particular month. If that's a January, obviously the value of the that month will be 31, and this is the load. I mean total load on the system. Right. Similarly, the next parameter was X bar. X bar is again very similar to that this one, but only the difference is it is multiplied with the value of 1000 and a delta T. I think this is similar to PL, right? So once you have, I mean, since the solar load fraction is a function of 4 variable, that was phi max, right? And then we define y, then the X bar, right? So if you know these parameter, I mean, let's say if you know the phi max and the y, you multiply that and you will get one factor, phi max bar. Then you also need the X bar, right? And X bar you can calculate from this value. Once you have the value of phi bar max into y and X bar, you can use those values to read from the graph, right? So, and then you can read the value of the phi value. Basically, these equations are plotted. I mean, this relationship, this correlation is plotted in the form of graph for different storage capacity. So this is a storage capacity. RS is a storage capacity. If you use different storage capacity, they have the different graph. So as you can see in the first graph, this graph is for a storage capacity of 175 kilojoule per degree per meter square of the collector area. So if the storage capacity of your solar heating system is this one, then if you have these two, I mean the vertical axis value and the horizontal axis value, you can read the value of the solar load fraction. So that will basically give you for one particular month, and once you have, you can calculate for all the month by using the same formula, and then finally you can evaluate the performance based on the annual. I mean, what is the annual solar load fraction? So this 50, I mean 0.5 is basically representing that out of your total load, 50% load is compensated by that installed solar heating system. Similarly, if the storage capacity is different, let's say this graph is for a storage capacity of 350 kilojoule per degree C per meter square of the collector area, and the next one is for, I mean, for large storage capacity for 700 kilojoule, and similarly the next one is 1400 kilojoule. So that means you have 4 different storage capacity, and you can calculate the value of the solar load fraction. So is it clear to everyone up till now? Okay, so let's try to solve one numerical problem. Evaluate the long-term performance of the following solar heating system. So let's say you are given one of the solar heating system, and you need to calculate the long-term performance. Long-term performance means on monthly basis as well as on the annual basis. The given data is that solar energy system is installed in Omaha, whose latitude is given to be 41 degree, requires energy above 60 degrees C. So that's the minimum temperature, right? Above 60 degree, at least this is the minimum. So this is T minimum, right? At a rate of 12 kilowatt for a 12-hour period each day. So this is the load. Load is 12 kilowatt. For 12, you can multiply that, you can convert it into kilowatt hour, and then you can divide with 3600 to convert into joule per second. The average ambient temperature and the monthly average temperature on a horizontal surface are given in the table below. So you are given for that particular location what is the average average value is given. For example, this is the extraterrestrial radiation, and this is the average ambient temperature for the January. This is the average terrestrial radiation. Basically, these are the parameter that you can have based on the location. So I mean, even for TOPI, you can get this data, that what is the average temperature in January, February, and so up to December, right? And similarly for the value of the terrestrial radiation and extraterrestrial radiation. And the collector properties, these are basically provided by the manufacturer. For example, you are given FR is basically the heat removal factor and the product of tau alpha, and the value is 0.72. Similarly, the product of FR into UL, the value is 2.63 watt per meter square per degree C, and the FR is equal to 0.8, and the product of tau alpha, I also explained this, that how you calculate this one. I mean, let's say if you need a tau alpha, and from tau alpha, and how you calculate. This was discussed in our previous slide. Similarly, the value of beta, which is the tilted angle, right? Collector surface area is 50 meters square, and the storage tank holds 4,180 liters of water. So this data is normally given, right? Before you evaluate the performance of any solar heating system, you must have data related to that installed solar heating system. Now, next is, to get the performance, let's say we calculate for 1 month only, let's say for the month of January, and then we can adopt the same procedure for the remaining month, and then we can have the average value for the F, weightage average value for the small f, and then we can calculate the capital F, which is the annual solar load fraction. So to calculate for the January, as we know, this is the parameter. For this parameter, what we need the value of from the graph. You know that we need the y-axis. On y-axis we have phi max y, and on horizontal axis we have x bar, right? And we also need the storage capacity, because every graph is designed for a particular storage capacity. To get the phi max, this phi max, what we need the value of the ABC coefficient, XC minimum, and then the value of RN and R, right? And we know the X minimum we can calculate from this value. We are given the product of FR and UL. We are given 60 degree C, the minimum temperature. And let's say for January, we are given the average ambient temperature, right? The value of FR is also given. The value of the product is also given, and these value we can calculate from the given. We discussed in the previous slide. KT also we discussed from the in the previous class, how we calculate the KT, and then based on this, let's say we are given for the month of January the value of HO. Similarly, we can calculate from that the value of KT, right? And then we can calculate the value of HD, ratio of the HD and H, and then we can calculate R. These value we can calculate from the relation that I showed you in the previous slide. So after calculating this, we can calculate the value of Rn, I mean the same relationship that I showed you in the previous slide, and then the ratio of the Rn and the R, because that ratio will be utilized here, right? So RC minimum is we can calculate from here, and this is the ratio. So now RC minimum will be, I mean if we put this value, the product of FRUL, T minimum is 60, the average ambient temperature is given. So if we put all these value, we can get the value of XC minimum. So this is the XC minimum. So if we put this XC here and the value of this ratio, we still need ABC. Those coefficient are as a function of KT, this value KT. So we can get those coefficient ABC as a function of KT, and then we can get the value of phi bar max. So the value of the phi bar max is equal to 0.51, and we still need the value of the X bar, right? And the value of the X bar and Y, and the value of, because we need the product of the phi bar max into Y. So Y, by using this formula, we know all of the value. Collector surface area is given, FR value is given, the product value is given, HT value is given, and the number of days for the January 31, and the load is also given, which is equal to how much kilowatt for I think 8 hours, for 12 hours, right? So you can put the values. The surface area is 50, and the value of FR is given, the product is given, HT is given. This is basically the terrestrial radiation, average terrestrial radiation for the month of January. That's also given. You can convert in joule, right? You can multiply that was in megajoule, and N is the number of days in January, and the load is also given, right? So you can convert into joule. So the value of the Y is 1.07. Now you can take a product of these. That will be Y max into Y. And then the parameter X bar, we can calculate from this formula. We are given all of the values, right? And we also need the storage capacity of this particular solar heating system. So which is equal to MCP per unit area of the collector. So that storage capacity is basically MCP, but we need per unit area of the solar collector. So that's 350 kilojoule per meter square per degree C. So that means for this, I think the graph A will be used, because graph A or graph B, we have to verify which graph will be used. Let me see that for 350, right? 350. Yeah, graph B will be used. So from this graph, I mean, if we know the value of the X bar and the product of phi bar max into Y, we can read the value of that F, right? So after calculating the storage capacity and the value of X bar and the product, right? X bar was equal to 2.19, and this product is equal to 0.54. Now we can read the value of the F from that graph. So the value of the F for the month of January is 0.52. So to meet the total load, I mean the total load was equal to 12 kilowatt. This was the total load for 12 hours, right? So to meet that load, the heating system that you have installed, that will give you on the monthly basis 52% of the load. So the solar load fraction is 52%. That means 48% you have to meet from some external source. Maybe you can install the electric heater or the gas heater. So you have to plan accordingly. So this was for the month of January. Similarly, we can calculate for the month of February, March, only the value of H bar, HT, and the ambient temperature will be varied. The same procedure can be adopted, and you can develop a table here. I mean, by calculating all of the unknown. So this is the F value from F value and the average total load. You know that you can calculate the average annual load, right? Okay, so that's the end of this chapter. Let's continue the next chapter, chapter 6. Chapter 6 is about the solar cooling and dehumidification. When we say solar cooling and dehumidification, basically solar energy has application in refrigeration, in air conditioning, and the desiccant dehumidification. When we say the refrigeration, that means to produce low temperature only, right? When we say air conditioning, that means low temperature and dehumidification, because there is a difference between the refrigeration and air conditioning. Refrigeration means only to produce low temperature only, whereas in case of air conditioning, along with the producing the low temperature, we have to maintain the humidity as well, right? And there are certain application where it is I mean industrial application, especially the industrial application, where you need a very less, I mean very dried air. So for that case we have to use some desiccant, I mean that can produce a very dry air, and the energy required for the desiccant is obtained from the solar heating system. So let's see each of the application. Let's say first of all the solar refrigeration. Now the solar refrigeration system, they are of two types, right? One is the vapor compression cycle, right? And another one is the vapor absorption cycle, right? I hope you are familiar with the vapor compression cycle. In vapor compression cycle, as you can see in the diagram, that consists of the evaporator, compressor, condenser, and expansion valve. So mainly it has four major components. When we say that this system is based on the solar energy, basically the energy is supplied to compressor only. Here the input energy, I mean that work input, is supplied to the compressor only, and that work input can be supplied with the help of the photovoltaic system, because to run the compressor it must be connected with an electric motor, and the input to the electric motor is it can be through the photovoltaic system, or it can be connected with an engine which is powered by the solar energy. So it's up to the design that how you are operating the compressor. So once you give that input to the compressor, basically what is happening in the vapor compression system, I assume that you are familiar with the vapor compression system, so I'll not go more into into the system. Basically in the evaporator, what is happening, the liquid refrigerant enters here, right, and it absorb energy, right? So when it absorbs energy, so it changes phase from liquid refrigerant, it becomes the vapor refrigerant because of the absorption of the energy. So this is a phase change process. And when the vapor enters into the compressor, it increases the pressure and the temperature. So the high pressure, high temperature vapors, they enter into the condenser, right, where we have to remove the heat. The heat absorbed in the evaporator, and as a result of the compression process. So these two sources of the heat we have to remove, we have to reject to the atmosphere. So to reject that heat, we can have the condenser either based on the cooling water, or it could be based on the air. So that amount of the energy that was absorbed in the evaporator is rejected to the atmosphere in the condenser, and then again we have the high pressure liquid refrigerant. So the pressure is very high, so that's why we have to lower down the pressure. When the high pressure liquid, you know, that process which is called the Joule-Thomson effect, when the high pressure liquid is suddenly expanded, then what happens, its temperature decrease a lot. But we have the mixed one, I mean here we have the mixed vapor and the liquid refrigerant, but the temperature is very low. So that low temperature mixed refrigerant is entered into the compressor again, and then this process keep on continuing. So what we need to know, basically we need to know in that vapor compression system, that what is the value of the work input required from the solar system, right? So how much energy input is required from the solar system? So we can calculate that by using the fundamental theory, which is called the energy balance, right? This is the vapor compression cycle. As I mentioned in the previous slide, that we have to use some property diagram, because the phase is changing, For example, from 1 to 2, this is the compression process, ideal isentropic compression. And then from 2 to 3 is a constant pressure heat rejection. And then from 3 to 4 is isenthalpic process. And then from 4 to 1 is the heat absorption in the evaporator, right? This is the pH diagram and this is the TS diagram. And by using the energy analysis, as you can see, by using the energy analysis of the vapor compression refrigeration system, we can calculate the amount of work input required for the compressor, right? For example, for the compressor, as you can see, we can have the energy balance for the compressor. For example, if we look at that, what is the energy entering and what is the energy leaving for the compressor? For example, here, this is the energy entering, this is the energy leaving, and this is the work input. So basically the energy entering is basically the enthalpy in the form of H1. Similarly, the energy leaving is H2. And similarly, the work input is W. So energy in is basically H1 plus W, that should be equal to H2, right? For the compressor, I mean energy in should be equal to energy out, right? So energy in is basically the H1. I mean this is the if you multiply with the M mass, this is basically kilojoule specific enthalpy. If you multiply with the mass, it will become the total enthalpy. So MH1 plus W, that should be equal to H2. So from here we can calculate the value of W, which is equal to the difference of the enthalpy. I mean M dot H2 minus H1. Similarly, for other component, for example, for condenser, we can have the energy balance, that how much is the energy entering. The energy entering is, for example, H2, energy leaving is, let's say, H3, and similarly we have to reject heat. So that's basically the heat rejection, which is QH out. So for this one, we have the energy in is H2 and energy out is this one and the QH. So QH, I mean heat rejected, we can calculate by the difference of the enthalpy. Similarly, for expansion valve, this is called the isenthalpic process in which the enthalpy remains constant. I mean H3 is equal to H4. This is an isenthalpic process. And lastly, for the evaporator, I mean energy balance for the evaporator mean what is the energy entering, what is the energy leaving, and similarly in evaporator energy is basically absorbed. So if you apply the energy balance, that means the H4, this is the energy entering, similarly plus the QL is the energy entering, so energy leaving is H1. So from here, I mean QL is the difference of H1 minus H4, right? So for the entire refrigeration system, we can evaluate the performance. We know that what is the input and what is the output. So we use a term we call this COP, coefficient of performance. So the coefficient of performance, or the COP, is basically the ratio of the heat absorbed to the work input, right? So COP of the system, we can have, this is basically the energy balance for the whole system, for the complete system. As you can see, I mean, if we take this as a whole system, so what is the energy balance for the complete system? From here, condenser energy is going out. Similarly, for evaporator, energy is coming in, and similarly for compressor, W is coming in. So that means in is the W plus QL, and what is out? QH. So from here, even we can get a W. So W will be QH minus QL. Right, so then we can have the coefficient of performance of the complete refrigeration system, which is the ratio of the energy absorbed to the work input. So energy absorbed is basically we calculated QL, that was equal to this value, right? And the value of the W work input, that was calculated to be this value, right? And similarly, we can have the isentropic efficiency of the compressor if that compression process is not the adiabatic. I mean, because the work input in a isentropic process is less compared to the actual work input. So this is the ratio of the isentropic work input to the actual work input. right? And then the second type of the system based on the solar energy, it is called vapor absorption cycle, right? This is the three component are the same, like evaporator, condenser, right? And the compressor, the single component even the expansion valve, the compressor is replaced with this system, right? With that system, right? The single component, and basically this is a compressor for the vapor absorption cycle, but this compressor is a thermal compressor, right? Basically the objective of the compressor is to increase the pressure of the vapors. So similarly, this is a mechanical compressor. This is called the thermal compressor. It is also used to increase the pressure of the vapor. As you can see, this is consist of the absorber, a small pump, and a generator. The major heat input in that vapor absorption system is in the generator to generate the vapors, right? So basically this heat is supplied through the solar energy system. The working principle is same, like as you know, in the evaporator, the heat is absorbed, and that heat absorption could be from the any load, any cooling load, or it could be cooling load of some space to be cooled, or it could be the chilled water. Any of the application could be to produce the cooling requirement. So once that refrigerant vapor enter into the evaporator, into the evaporator, it absorbs that heat. So as a result, the liquid refrigerant is converted into vapors. Those refrigerant vapor, they have low pressure, so they are absorbed in an absorbent, right? So the mixture of the absorbent and the refrigerant, they are pumped into the generator where you apply the heat. So heat basically separate refrigerant and the absorbent. So the refrigerant vapors, they are at high pressure because of the absorption of the heat, and the concentrated mixture of the refrigerant and absorbent, it go back to the absorbent. So those high pressure vapor of the refrigerant, they again move to the condenser where they reject the heat. The heat absorbed in the generator and heat absorbed in the evaporator, that is rejected in the atmosphere. So after expansion, isenthalpic process, again the liquid refrigerant come back into the evaporator. So this process keeps on continuing. So this is basically the solar absorption system. As you can see, the major input required is in the generator, where you have to where you have to separate the absorbent and the refrigerant. So that heat is basically supplied with the help of a solar collector. Normally, the temperature required in the generator is in the range of 70 to 80 degrees C, right? So you know that this is very simple for the solar collector to produce this type of the energy. So this absorption chiller or the vapor absorption system, they are very ideal for the solar collector or to utilize the solar energy system. You can adopt the same procedure to analyze that how much energy is required. Basically, our objective, if we are using the solar heating system, that how much energy is required in the generator, we call the QG, right? So that's basically the requirement for the solar heating system, right? Basically, in solar heating system, there are two combinations that are being utilized. One of them called the ammonia water, right? Ammonia water, in that case, ammonia is the refrigerant and water is the absorbent. And the second type of the system, it's called the water lithium bromide system. In that system, water is the refrigerant and lithium bromide is the absorbent, right? And there is a criteria for the absorbent, that it should have a greater chemical affinity for the refrigerant than that indicated by the ordinary law of solubility. So that's why we choose water as the refrigerant and the lithium bromide as a salt, because water, it has a greater affinity for ammonia, right? And similarly, the lithium bromide as an absorbent, because it has a greater affinity for the water. There is a rough estimate that the quantity of heat released in the absorption is a crude measure of the chemical affinity. If the heat release is very high in the absorption process, that means that has a greater affinity for the absorption. But generally, there are so many range of the refrigerant absorbent combination, but majority of the system, they are based on the ammonia water or water lithium bromide system, right? So the first one is lithium bromide water absorption refrigeration system. As I indicated that in lithium bromide water absorption refrigeration system, lithium bromide is the absorbent and water is the refrigerant. So when we are using water as a refrigerant, that means these systems are also called absorption chiller, right? These system, when you are using water as a refrigerant, you cannot produce cooling below 0°C because water cannot be used as a refrigerant for below 0°C because it will freeze, so it cannot move in the system. So this type of the system can only be used for the application in the air conditioning and chilling process. I mean, first you can produce the chilled water, and then from chilled water you can produce air conditioning. As we are producing in GIK, what we are doing basically, we are producing the chilled water in the HVAC system, and that chilled water is sent to various building where they have installed the air handling unit, I mean the cooling coil. So as a heat exchanger between the outside air and the chilled water, then the cooling air can be produced in various building. And similar during the winter, the hot water is sent to the building and in the air handling unit. So as a heat exchanger, hot air can be produced in various building. Anyhow, we are talking about the application of the solar energy for the cooling system. So this system based on the lithium bromide, they are present in various sizes. For example, 10 to 100 tons of refrigeration. This is not the weight. As you know, the size of the refrigeration system is measured in tons of the refrigeration system, right? The lowest evaporation temperature of 4°C can be produced by using the lithium bromide system. Normally the absorber, they are operated under vacuum, right, at a temperature of 0.8 kilopascal, because lower the pressure, then that means low will be the boiling point. So that means even if the small amount of heat that the refrigerant has to absorb, it is possible because inside the vapor pressure is low, so the boiling point of the pressure is low. The second system, the second vapor absorption system is ammonia water combination. In that case, ammonia is a refrigerant and water is an absorbent. When you use ammonia, I mean that system is used for cooling and low temperature freezing. I mean applications below 0°C, right? Applications below 0°C. So ammonia will quickly corrode the copper. That's the disadvantage of that. But when you need to produce temperature below than the 0°C, I mean in case of lithium water combination, you cannot produce temperature below 0°C. But when you use ammonia as a refrigerant, you can produce temperature below 0°C. But this system has disadvantages as well because ammonia is very crude, so it can corrode the copper, aluminium, zinc, and other alloys. So that's why for choosing the material, this is recommended that you can use the steel, cast iron, or SS, I mean stainless steel, or you can use different plastic as well, which are resistant to the ammonia. I think we keep up till here. We'll continue in the next class. If you have any question, you can ask me.